All right, so in this video, we begin section 8.3, but we don't finish it, all right? So why don't you pause, copy this panel down, and then press play. So in section 8.3, we move from having one sample and doing a test of either the mean or proportion of success to having two samples and doing such a test, okay? And in this video, we're going to look at the two sample t-test for difference of normal means. So we're going to stick with means. We're going to say the populations are normal and do figure out how to create p-values for this, right? So in our setup, I have one population that's normal mu1 sigma 1 squared, from which I have data points x1 through x of n1. And then I have a second population that's normal, mean mu2 and sigma 2 squared for mean standard deviation. And I have random variables y1 up to y sub n sub 2 from that population. The two populations are independent. The sample means and standard deviations are given by x bar, s1, y bar, and s2. Okay. And I have a null hypothesis that the means are the same for the two populations, and the alternate hypothesis, two-sided, they are not. All right. And we're going to use a t-statistic, which makes sense, right? So please note, we do not know sigma 1, we do not know sigma 2. So we can't use our normal testing procedures. So since the data is normal and I don't know the variances, I will appeal to t-distributions, okay? So I'm setting up my t-statistic, and it looks slightly different, but it's the difference of the two sample means divided by some measure of like the average standard error. So the square root of s1 squared over n1, that'd be the standard error for the first sample, for the first random sample. Square root of s2 squared over n2, that'd be the standard deviation for the second random sample. So I'm going to add them together somehow, and that's sort of like an average of the standard errors. So that's my test statistic. Given the random samples, I can calculate the observed value of it. And then this result says that under the null hypothesis, this test statistic has an approximate t-distribution, okay, with script v degrees of freedom, where unfortunately script v is this monstrosity here, okay? So I have s1 squared over n1 plus s2 squared over n2 all squared, and then the denominator is even more unpretty. I've got s1 squared over n1, quantity squared, divided by n sub 1 minus 1, added to the exact same thing with the 2's in it in the second sample. Okay, so there's your degrees of freedom for the t-distribution that this thing approximately follows. And then to get the p-value, I'm just looking at the probability that chance alone would produce a test statistic as extreme or more extreme than what we observed. Okay, so I'm going to do the usual two-sided thing and calculate the probabilities. And we'll do an example of that in the next board here. And again, you don't have to worry about memorizing that thing. We got a note card, we can copy it down, right? Okay, so I will be appealing to R for this one. But background, we're looking at that North Carolina birth weights file again. And now we're going to look at two populations from within that file. I could imagine that I've got two populations of mothers in North Carolina who gave birth. One is the population of non-smoking mothers. The other is the population of smoking mothers, okay? And they might wish to compare the weights of the birth weights of their children or their babies, okay? So I have n sub 1, I have 898 non-smoking mothers' babies. Their average weight is 3472 grams, and their standard error for the standard deviation was 479 grams. Now, for the other population, there's 111 babies whose mothers were smokers. Their average birth weight was 3257, and their standard deviation was 520 grams, okay? Now, null hypothesis, smoking has nothing to do with birth weight, okay? So stay conservative, assume the means are the same. Alternate hypothesis, well, it sure looks like the non-smoker babies weigh more than smoker babies, okay? Now, I can compute the difference in x bar and y bar as 215 grams. I can compute this test statistic by hand as 4.14, and I can compute that script v, the degrees of freedom, by hand. I got 134.011, okay? So I didn't show you the computations, but you know, we've got the four numbers that we need to grind through those things. So to get the p-value then, since it's one-sided, the p-value, p-value is what's the probability that this test statistic or something more extreme could occur by chance under the null hypothesis. So under the null hypothesis, this guy follows a t-distribution with this many degrees of freedom. So what's the probability that a t-distribution with that many degrees of freedom can have a value exceeding 4.1411? Okay. Now, I hand it off to R to tell me the answer to this. So P is the probability at or below the mark. So I'm going to do 1 minus P since I wanted above it. T is a t-distribution. There's my mark. There's my degrees of freedom. And R returned 0.00003. So that's less than 0.003%. It's way below 5%. It is statistically significant. So we could conclude that, yeah, you know what? We're going to reject the null hypothesis. This is so far below 5%. There's no way that value could have occurred by chance if the null hypothesis was true. It occurred, so the null hypothesis cannot be true, and we'll conclude that there's great statistical evidence that babies born of smokers weigh, on average, less than babies born of non-smokers. No alternate hypothesis. Okay. Now let's go to R because it can do all of this by hand in one step. So I might as well show you that. Okay. So we'll switch over to R if my computer is willing. So we're in sample 8.5 here. If you like, make sure you got that resample clicked off under packages. You can look at the birth weights data again if you wish. And you get the mother's ages, you get alcohol, tobacco, the gender of the baby, the weight of the baby, smoker or not smoker, okay? And so we're going to be focused on smoker, the smoker column, and the weight column. All right, so let's go back. And here's how we do on line 50, how we do all this t-test in one step. T.test, we're comparing weight with smoking, the data stands verse 2004, and the alternate hypothesis is greater. We'll see what that means when we run it. Okay, so it tells us this is a Welch two-sample t-test, which just refers to the specific algorithm that R is using to grind this t-test, okay? Gives us our t-statistic, gives your t-statistic 4.1411, the degrees of freedom 134.01, and the p-value basically 3 times 10 to the negative fifth, just like we had. Also gives you a 95% confidence interval that states the alternate hypothesis is the true difference in means between group no smoking and group yes smoking is greater than 0, okay? So that would be mu1 minus mu2 is greater than 0, which is equivalent to our alternate hypothesis. Okay? So that's how we can do it all in one fell swoop. Okay. There's on line 57, which is my command for how I computed that probability under a t-distribution earlier. And that's where I got the 3 times 10 to the negative fifth. Okay, so let's stop sharing and sort of some concluding remarks. Okay, so pause, copy, and play. Ooh, seems rather small. All right, how about that? Pause, copy, and play. All right, so please know, under that t-test with 2 samples, there was a big assumption that was required. Both populations were normal. I didn't know the standard deviations or the variances of either one, but both of them were normal, okay? And if that doesn't hold, then maybe we should be thinking out about a permutation test or a bootstrap t-test, okay? Because if they're not normal, then a t-distribution probably doesn't mimic things very well. Now, last little point here about this guy, matched pairs. We constantly talk about what happens if we have 2 populations, but they're actually matched pairs. Well, we're going to do the standard thing. If we have matched pairs, we'll do our standard adjustment. First, we're going to take the difference between the pairs of data, and that's going to take us from 2 populations to 1, their difference, okay? And then I can analyze that difference via an ordinary t-test, if we think it's normal, or a bootstrap t-test if we think it's not normal, if we think the data is not symmetric or not normal. Okay. All right,